Right, so here's the Python code that we are writing for the response of our linear systems. And here you can see some of the libraries that I'm making use of. So of course, NumPy. We will also use SciPy because we are actually going to integrate our function. So dy dt is some function of y and u. We are going to integrate that differential equation. So we'll use the integrate library in SciPy, specifically ODE integration. Of course, matplotlib for the plotting. And I'm also importing some animation stuff because I actually want to use, I want to be able to adjust the parameters of the equation, and we'll be able to drag a little widget and see live how the system responds. So we'll actually be able to drag this and see, oops. So we'll drag this and then we'll be able to see how the process responds as we change some of the parameters in our systems. Okay, so so let's look at the first one. So here, here's my differential equation. Maybe just a quick tour of the code. I tried to keep all my constants in one place so that if I want to adjust anything, then I can do it in one place. And then I'm also defining all my equations here. So you'll find the differential equations here. We'll look at this in more detail just now. And down here is where I'm calculating the response and just plotting it on the screen. And calculating the response is simply here. I'm just integrating the differential equations. So I specify that the differential equations are stored here, and we have to give some initial condition. I think I just set that to a 1 here. And then, yeah, here's where you connect your sliders. So our parameters A and B, we'll look just now at what those are, but we can drag around A and B, and those will be received in this function, and then they'll go into the ODE function. So they will affect this equation. So we solve the differential equations here, and then we can just plot those results, and you can read through this and see what that does, setting the axes and changing the intervals and so on. So the first one we'll look at is, yeah, let's just do tank step. So this is the tank problem. And so in the tank problem, this is simply dv dt equals q in minus q out. And in this case, yeah, we are applying a step function. So here, our value A is going to be the point of the step. So before time equals A, we'll have that the inlet flow equals the outlet flow. And then after T equals A, the inlet flow becomes B. So we set a value for B, and that value becomes active only after the time is more than or equal to A. And here, this is not the same as the tank problem we saw before. So it has Q in here, but our exit flow rate is dependent on the level. So here the tank level is Y. So there is a dependence of the rate of change of the tank level, right? dy dt is the rate of change of the level. That is dependent. So the exit flow rate is dependent on the height of the level. So if you imagine a column with the liquid level in it, then the higher that liquid level, the faster will be the exit flow. Of course, if it's a gravity-driven exit flow, then it will be proportional to the square root. But anyway, for simplicity, because we want to work with the first order process, I'm just making it directly proportional, right? So it's a little bit of a cheat here, but anyway, we'll get to see a first order process. So that's basically the system we are dealing with. And if you look at the plot here, let's actually just get this to slightly better values. So let's say we have a negative value for A. So if A is negative, and if we look in our differential equation, if A is negative, it's this one. So if A is negative, then that means the process, because we are integrating from 0 upwards, that means the step has already occurred far in the past. Well, not really far in the past, but the step has already happened. So we are not seeing a kind of step, we can't see a discrete change in our responses yet, because the step already happened before we started looking at the system. So if I adjust this forward, so now it's on 0, so the step is happening on 0, we still can't see it. Now if we start bringing it in here, you can see the step is moving in here. So here's 25, let's try and get it further in. So the step, so this picture just has to catch up a bit. So we are applying the step, let's get it to a nice 50. So we are applying the step on 50. And so you can see that the system was steadying out. So it was reaching a steady state, but then we went and step changed it. And we step changed it, we said B is -3. So if we set B to -3, then yeah, our inlet flow becomes simply -3. So clearly that's going to be much lower than the original flow rates. So we the system was steadying out, but then we suddenly dropped the inlet flow, and now the system will settle out at some new value. And it settles to a negative value, which is not really possible. Let's look at more realistic values. Okay, so something like that. So we've step changed our inlet flow rate to a value of 4, and then the system settles out near this new steady state. Okay, so we can see that's the only possible thing that will happen in this system. It will exponentially saturate to a new steady state. You can see that there are more features than we saw in the notes, and that's because we are now looking across all the possibilities. So in the example in the notes, we were only looking at from the time of the step onwards. So now, of course, we've got some residual, some legacy behavior, but from the time of the step onwards, there's only exponential behavior, and we settle down to a new steady state. So this is, it's behaving as we expected it would. So from our analysis, we expected a certain behavior, and then you can think of this as our numerical experiment. So from our experiment, it is giving us that behavior. So that's our first order system. Okay, I don't have any other first order here. I want to actually derive the second order before we start playing around with it. But you might recognize this equation. So that's the first order form, and you can always rewrite any second order differential equation as 2 first order differential equations. And if you look at this, this is the equation of a spring. And in this case, if we run this, and by the way, it's the same setup. This function is largely the same as above. You've got slightly different constants here. And if you look here, these are the same as these equations. So you can say dy1 dt equals y2. So here we have dy1 dt equals y2, right? Y brackets 1 here, that's referring to the second, right? 0 is the first and 1 is the second. So this is dy1 dt equals y2. So dy1 dt is y2. And then similarly here, dy2 dt, right? The second one that we append is equal to a y naught. So a y naught plus, minus b y1. Here, this b value, I guess we need to change the sign here or here. So you can play around with the a and b values, and you'll find that you can get all kinds of different behavior here. So we'll talk a bit about why all these things happen in this case. So let's first derive a second order case. So going back here, yeah, let's look at this case. So we'll again take a tank's level problem. So that's one of the simplest we can think of. And we are looking now at interacting tanks. So we are feeding into the first tank, and the height there is h1. And this time, the height is driving the flow, right? So like in the simulation, we have the exit flow rate from the first tank is proportional to the height in the first tank. So that's why the model looks like this. The rate of change of volume is equal to the inlet flow rate minus the height multiplied by some constant or divided by some constant. So that's the balance on the first tank. And now let's look at the balance on the second one. So the rate of change of the liquid volume in the second tank, that is equal to the flow rate coming in here minus the flow rate exiting here. So the flow rate coming in here, we've just said is equal to H1 divided by K1. So in this case, it's a plus H1 divided by K1, right? That flow is contributing to the volume here. So that's a plus there. And then we are losing volume from the second tank when it flows out here. And again, that's driven by this weird not gravity, because it should be square root, but we want to keep it first order or second order. So anyway, it's H2 over K2. That's your exit flow rate here, right? So that's H1 and H2. And if you think about this, we can see that the control action or the manipulated variable action is here in the first tank. And the response in the second tank is through this intermediary of this stream here. So this stream does have a first order response with respect to this stream. However, the flow rate out here or the height here is then influenced by this first order. So there's a cascade of orders here. So there's a first order response we expect from here, but that is delayed by a first order response from the first tank. So overall, this we suspect this would be a second order response. And we can apply the approach that we used last time based on deviation variables. So we can say, well, hopefully the system was at some steady state to begin with, and we'll define that steady state as being the heights, the steady initial height, h1 over bar and h2 over bar. And also we are defining when we were at those steady states, then we were at some initial inlet flow rate. And so this Q naught, it is an inlet flow rate, right? A specific value of the inlet flow rate. And so we are saying our current deviation variable, or our current flow rate in, is Q in of t. But in terms of a deviation variable, we'll write it as our current one minus that initial one. And if you make all those substitutions into your equations, right, you can read through all this or work this out yourself. We'll see that we get to a nice simple form that looks like this. So eventually everything is written in terms of deviation variables like this. And we know that the initial condition, the reason that we are doing this is we are trying to get initial conditions of 0. So if we do that, and then if we Laplace transform these equations, right? So we can say this is going to be SH1, and the initial values. By the way, this should say something like initial. Yeah, so this is only true initially, right? You do have H1 dashed, which is not 0 at other times. Right, so so we get rid of that, and now the left-hand side simplifies. It becomes a form just like that. So normally when you Laplace transform the derivative, you have an extra initial value hanging about, but now we proposed it as a deviation variable, so we don't get that. So the left-hand side is nice and simple. And then the right-hand side will simply be the Laplace version of this. So that's Q, and then here the h is Laplace transform. So those are functions, Laplace functions as well. So now we have from the first equation, we can group out an h1, right? You've got h1 here, you've got h1 here, and you've got the q there. So you can relate h1 to q. So you can define your transfer function g on the first tank as g1. So we have h1 divided by q, and just using this equation, h1 divided by q is 1 over this stuff. So that's there. And then, like we said before, this is a first order form. So you can see if you were to, let's say, we just multiply top and bottom by k1, then you'll get k1 here plus 1 down here, and then the k1 a1. So we can say we now have this familiar form. So we can say tau here is k1 a1, and then the capital K is that k1 there, right? So we've got the typical first order response here. And by the way, we are writing this as tau1 because we know this is still just talking about the first tank, and we anticipate we'll need another tau2 over here. Okay, so that's the first one taken care of. Now let's look at the second equation. So again, if we look at this, we can replace this by S capital H2. We can replace that by capital H1 and that by capital H2. So we've done all of that here, and then we group, here, and then we group out the H2, and then you get that. And for H1, we can go ahead and substitute what we get here. So we just have to multiply Q here, and then we've got that response. So we can rewrite this whole thing. We've gotten rid of H1 now. We can rewrite this as H2 as a function of Q. So there's now H2 as a function of Q. And again, we've got this form here. And if we multiply top and bottom by K1, we'll get, by K2, we'll get K2 over K2A2S plus 1. So now we've got that nice familiar form here. And this is where tau2 is equal to A2 times K2. Okay, so we now have the response of the second tank. And you can see we've got 2 of these nice denominator factors here. So that's our second order response. Okay. So we can show then, generally speaking, all our second order processes will have a form like this. And by the way, this was a very kind of explicit second order dependence. If you have some differential equation, maybe let's do a quick example here. If you have a second order differential equation, let's just take something like this. So let's say we have d2y dt squared plus a times dy dt plus b equals c. So let's say we had a second order differential equation like this. Then we could always convert this to a system of 2 first order differential equations. And to do that, we'll propose 2 new variables. So we'll call it y1 equals y. It's a little bit of a silly thing, but anyway, that's how I typically do my, my conversion. So we'll set y1 equals y, and we'll set y2 equals dy dt, right? So y1 and y2 are now completely different functions. They have no relationship with y. Well, they do through this now, but before we wrote this, we just regard y1 and y2 as different functions. So and dy dt, even though that's a derivative, if the function y, if we differentiate it, we'll get a new function. So we are just calling this new function y2. So I'm just trying to say there's nothing specific about this. This is just general. This doesn't make anything, we don't lose any generality by proposing this set of variables here. So we've just created new arbitrary variables like this. And so one of these we can rewrite a little bit differently. So we can take this and we can rewrite this as we've said y1 equals y, so we can just rewrite this as dy1 dt. And maybe let's just rewrite this as equal to y2 instead. So that's equal to y2. So just move that to the right-hand side there. So that's one equation. And now if we take this equation, let's just copy it here first. Now, if you look at this, this first term, d2y dt squared, we can think of this as dy2 dt squared. So we can say dy2 dt, right? So if you think about it, if you look here at y2, if you take d dt of y2, then it will be d2y dt squared. So we can just replace this, the second order derivative, by a first order derivative in y2. And that's basically that's the basis of the whole method. This dy dt is of course y2 by definition of y2. And there, now we have two first order differential equations. And now we have two equations, and we recognize now we have again a second order system, and the second order system is going to have this eventual transfer function. So all second order linear ODEs have this transfer function, and any process with two first order functions also have this, this form. So now we can say we have the general form for all second order processes, and they arise in different ways. But as long as it's second order, we know every possible thing there is to know about its transfer function. Now, there are a couple of interesting things that happen in our second order processes that don't happen in the first order case, right? The first order case was kind of boring. If you think about what happened with the step increase, it just exponentially went up and saturated to a new steady state. So let's see what happens in our second order case. So if we apply a step response, right, a step input, so U looks like this. So our overall process looks like this, right? It's so we've just moved the M across here, and it's still 1 over S times this stuff. And by the way, here, this looks a little bit different. We know that our second order process always looks like this, but what we are going to do is just propose that instead of writing it like this, right, if you multiply this out, it is going to be a quadratic, right? You'll get tau 1, tau 2 s squared plus tau 2 s plus tau 1 s plus 1, right? So that's going to be our, if we multiply it out, we'll get a slightly different arrangement of our taus. So we can say, well, by the end of the day, it's going to look like a second order polynomial. And so we can propose, instead of tau 1 and tau 2, we can propose a tau squared in this position. And then we can also propose another new constant here, a zeta, so 2 times zeta, and then this new variable tau as well. So currently, we don't know anything about tau. Currently, we know how to get tau 1 and tau 2. But of course, if we just multiply it out and compare it with this new form, we can see how to calculate tau 1 and tau 2. So that's the new form that we want. And obviously, this is not just chosen to make things look weird and with Greek symbols and all abstract. There are some nice reasons for proposing this. So we'll find these parameters, zeta and tau, very useful parameters to play around with. So there's a reason that we use 2 over there and a zeta. It's because we can really make some nice general comments about our second order systems. So that's where this weird looking new form comes from. It comes directly from our general formulation here. So, so we've got that new form, and we are looking at a step response now. So we've got the 1 over S there and the M over there. And now when we analyze this, when we apply a step, you will actually get an oscillation under certain conditions. So if you think about our process, right, the example that we were looking at, the one that we used to derive and show that we get this general form. So if you look back here and think about the things that can happen, right, if you apply a sudden step here, right, you are basically creating a wave that will enter this system. It's going to create a disturbance here, and it's going to cause a disturbance that will take some time for the system to get over. So you are going to get a response here that you are going to get that this level is going to be increasing, and it will take some time to increase to a new steady state. So while it's increasing here, this system here is also going to experience an increase here. So your inlet flow rate here will start going up. And so you will get a rise for a while here, but the rise comes here a little bit slower than it comes here. So because it's a second order process, there's a certain delay between these two tanks. So this will experience a certain rise, but then what will also happen is the exit flow rate will start to increase. So because your inlet flow increases here, the volume starts to increase, then your exit flow increases also. So your level here will rise, but as this level is rising, here your system that's feeding it is settling down to a new steady state as well. So this height change, there is a height change happening here as well. So if you like, the driving force, the entry flow rate here, even while this level has built up to a high volume, the inlet flow is now reducing here. It's steadying out to a new steady state here. And so this flow rate will start to go down. But now you've already reached a high volume here. And so you've still got a high exit flow happening here. So then your level here will start to go down. And then it will go down because you've got initially such a high volume here. Your flow rate out here is going to be quite high. And it's going to end up that this flow rate actually exceeds the inlet flow rate here for a short while. And so, so this is going to start to drain the tank. And then this level eventually goes so low that this flow starts to then cause us to accumulate again. So, and I'm starting to go in a circle because you can see that it's the bobbing around of these between these two tanks, because there's a certain time delay here. Then this is going to bounce around a little bit before it settles down to its new steady state across this whole thing. So that's what's happening here. That's why even for a simple step input, we can get a situation where it bounces around a bit before we get the new steady state. So that's what can happen in our second order case. So second order, because we have second order, there is a certain delay between the manipulated variable action and our response. So we can see now that it's possible for oscillations to occur in our system, in our process, even though our input was just a step response. So be careful of that. We did not yet apply a sine wave, but we are seeing a sine wave on the process response. So we've applied only a step input, but we are seeing a sinusoidal-like response from our process. And that's just because of the delay between the two states there. And because we've taken care to write it in this form with this tau and this zeta, the reason we've arranged it this way is that it turns out that zeta equals 1 is a critical value. So if we are just above zeta equals 1, we don't see any of that bouncing around, right? When zeta is greater than or equal to 1, then we get an exponential type behavior. So remember, the first order processes had an exponential settling down into a new steady state. And it's not exactly a pure exponential. There is actually a little bit of S curving here. And you can see some of that here. I can't really zoom in here, but this is actually an S. It's a kind of second order exponential transition from one steady state to another, but it doesn't involve any oscillations. So for values of zeta greater than or equal to 1, you get exponential transition without oscillation. But the moment you go below 1, you will get some oscillation occurring. And the smaller the zeta value, the greater the extent of the oscillation. And this is important for us to understand. So this is the kind of feature that we are worried about. So if it turns out that we are going to exceed our steady state, right? We want to reach some set point value, but it turns out we will overshoot that set point value for some time before before steadying out. Then it might be problematic in terms of the way we operate that unit. So for example, if this was temperature and if it so happened that we step up, we step increased maybe a steam flow rate or something like that, and we didn't realize the temperature was going to go up so high and that it exceeded the safety limits, then that would be a critical failure in our control strategy. So we do need to be able to analyze this. We do need to be able to figure out how high is it going to exceed our set point by? How long is that exceeded value going to persist? So that's the kind of thing that we are looking for. So even though this is not yet real control, right, because we are actually applying a specific time function, which becomes an S function, still it can give us some insight into the response of that system, and we'll be able to use that to design our controller. So if you look in the notes, you'll see we find out where we get this maximum value, and we can rewrite that in terms of the zeta value. And so we can go ahead and we do have control over this process. We can define controller values that cause zeta to be high enough that we don't get such extreme oscillations. So if we know our safety limit is here at say 1.2, then we know that we can design for a minimum zeta value of 0.6, and then that will translate to a certain controller value. Or it might even be that the process needs to change. We might need to change a volume of something, right? If you look back at the real problem, we have control over the areas in the tanks that does affect the time constants. So that's how we can use that information. We can redesign the process itself so it's more controllable, or we can design a better controller that can get us away from this problem of very bad overshoots. And again, it's always a trade-off. We acknowledge that these low zeta values are probably giving us nice fast control, right? If you look at this case where we are using much higher values of zeta, you can see the control action is much slower here. So that means we have to spend more time away from the desired set point. Whereas here, we find we overshot the set point, but we stuck a bit closer to that set point than here, where we just have to wait a very long time. So it could be that the best controller has a little bit of oscillation in it, and we just then have to control how bad that oscillation is going to be. So if you look in the notes, you'll see more analysis around this. We can find the point at which we get the maximum, and so we can we get a nice relationship so that we can control to what extent we overshoot and all those good things. So that's a kind of interesting thing we can see. Then again, well, we're not going to do the ramp function because, as I said before, the sine waves turn out to be extremely important for our controllers later on. So we are going to look at the sine wave input. So again, for our second order process, we've got this, this factor here. And then for a sine wave input, we have that. Again, the amplitude A of the sine wave and the frequency is omega. And yeah, it's shown nicely here. I should have actually put this up earlier, but the tau is the square root of the product of the two taus. So if you like, this is a kind of geometric averaging of the two tau values, the two time constants in our process. So a geometric averaged time constant. And then zeta is also related to the time constants like this. So zeta and tau are defined in this way. And then we showed also when we combined those two factors together and made a phi. So that's how you get phi. So phi is also related to the two tau values through zeta and tau here. Right, so the second order process, you can show that it has this response. So if you follow the development, try to do this by yourself. Remember, we'll try and separate this out into, right, we propose that this is equal to some constant divided by another constant times s plus 1 plus. So try a couple, in the notes I do derive this more fully, but try and do the separation yourself and see if you can get to this form. So anyway, that's the response that you get. And according to this, we will get a sine wave as the response. And we will also get an amplitude of the sine wave, which does depend on the applied frequency and on the two tau values. So we take this as the amplitude. So we can see that's the amplitude. And we define for ourselves an amplitude ratio. So that ratio is because the applied sine wave only has an amplitude of A, right? The applied sine wave, that's its amplitude A. So the response has that amplitude. So what we want to try to think about is, well, how does, what's the ratio of the response to the applied value? So the ratio we can get by dividing that by the Ka. So that's our amplitude ratio here. And again, that's dependent on the two time constants and the applied frequency. And so if you were to investigate this, so here's the same tanks in series problem. And here we are applying a, you can try different things. We can try the step or we can try the sign. So here, you just change the step to sign if you want to view the sign. So let's look here in our actual numerical experiment. So we are applying a step here, and this is our second order process. And let's just run this. Okay. And let's see if we apply these values, you see this is in the zone where zeta is all nice and stable. And then if I start reducing this, then the two switch over. And now you see we are actually in an unstable region of operation. And so the stability of the process becomes challenged. And so here, play around with this, see if you can get the sine waves. Yeah, I just have to carefully find a nice set of parameters where you see the sine waves. But that's basically the response that you can get. We'll come back to this later. This is plotting the transfer function, and it turns out that you can use this to figure out when you are in these danger zones. But anyway, at the moment, the constants, there does exist a critical set of values where you can see the sine wave a bit more, but here they are being overshadowed by the large movement here. So you can't see the oscillation too well here. I'll try to find a better set of parameters for this. But you can, that's how you can try out the sine wave, the step function. So if we just change this to the sine wave and rerun this, you can see here that your process is responding, of course, with the sine wave. And just try to see if I can get that for the other one as well in tank 2. But yeah, it looks like tank 1 is playing something of a buffering role. So because the applied oscillation, let's see if we increase this or decrease. Yeah, it turns out that here tank 1, because the parameters are not so well chosen. Okay, there we go. So, oops. Yeah, I've been dragging these a bit too quickly, but if you make the sine wave a bit more pronounced by using these values for the inlet flow, then you can see, you start to see the sine wave on the exit one as well. And like we showed, we can define the ratio of the observed amplitude to the amplitude applied at the inlet point. So the inlet amplitude, so if you read this part, you'll see how it's set up. So here I've created a function q in, so that's working out the applied function. So if we want to use the sine wave, then it's going to give us the sine of q in times t. So yeah, I was just a bit lazy to change this to omega, so I left that as q in. I actually wanted to share that q in naught, that variable, with the step side where it makes a bit more sense. But anyway, we are actually adjusting the frequency here with this q in naught. Should give us the same if we go on to +6. So we were looking at -6. So there's a positive frequency, and you can see a little bit that we've got the we are getting also a sine wave. Yeah, it's quite fine there. But anyway, you can play around with these parameters. You can try the step function and the sine function, and you get those responses there. Okay, so you can get the same response in the numerical results. So you can analyze it fully using the amplitude ratio. And so what we've got here are for different zeta values. So if you play around with all those constants enough, then you can generate different values for tau omega, and then you can find where the amplitude ratio goes to the maximum value. So you can look up the value of tau omega that maximizes the amplitude ratio. So remember, that's the danger point. There exists a critical tau times omega where you get the maximum amplitude ratio. So that's going to be the place where you get the highest exceeding of the new steady state. So now that we have an equation for that, we can work backwards and say, okay, if my zeta values are these, then that's where omega is going to give me the maximum value, and hence we can work out what that will be. And so we can start playing around with the tau values until we control how high this goes. Okay, and then we can talk a bit more as we go about how we can identify all this through our Laplace domain instead. Okay, and then also have a look at the notes on differential equations. This starts to touch on next week exactly what we said just now, using the Laplace domain to understand all this. So it turns out in the Laplace domain, you can figure out the time constants more easily. And so you can identify when the system is going to be unstable, when it's going to give us oscillations and things like that. So that's what we'll talk about next time. And that's it for today.